Hello, good evening. Let's wait for a couple of minutes, then we'll start. Okay, I think we can start now. So, good evening once again. My name is Umer Sen. I'm a PhD scholar at the Department of Mechanical Engineering at IIT Madras, and I'm here to take your doubt sessions for the course Finite Element Method, Variational Methods to Computer Programming. So, we have finished, uh, I think, 8 weeks now. We have so far done 8 sessions now. This is a ninth session, and so. So we started this course. So I'll just quickly give a brief that we started with this course with uh, a quick discussion on the variational principles in mechanics and how to pose a minimization problem, and from that how can we derive the governing equation for most of the problems. And then we with that foundation we moved on to the finite element method. We discussed in the basic structure or steps in solving any problem using the finite element method. Then we started with the 1D finite element method, and for that we solved some standard structure problems. So we started with the 1D bar problem, then then the stress problems, then beam problems, and finally we generalized all these different problems into single frame element problem. So that concluded the discussion of 1D FEM. Then for 2D FEM, we first did a quick discussion on uh, the uh, the vector calculus, and after that, the last 2 weeks we spent on doing the 2D FEM scalar problems. So I think the starting of this week, we conclude the discussion on the 2D FEM by discussing how to write a program, how program for 2D FEM scalar field problem works. So now we're going to start with the vector field problems for 2D FEM. And a classical example for a vector field problem is the elasticity problem. So can someone first tell me what is a vector field problem? Anyone?
The primary variable that we are solving will be a vector.
Uh, exactly. So now our primary variable is not just single field like in the previous problem we solved for a heat equation where we solved for the time temperature. So there was only just one field temperature. Now there can be more than one fields at a node. So this basically increases the number of degree of freedom per node. So now it's like a vector. So for example, for elasticity, we have displacement in x direction, displacement in y direction, displacement in z direction. So we are solving for all these three now. And maybe if we are doing thermoelasticity, then we also add a temperature field there and whatnot we can add there. So and as the number of variable increase, the number of equations would also increase. So for the classic elasticity problem in 3D, we'll have three equations. So let us look at how do we define classical elasticity problem, a linear elasticity problem. So first of all, we define a primary variable, that is the displacement field vector. So displacement field vector would have three components in each of the directions: ux, uy, uz. And then there's something called gradient tensor. So what is the order of this gradient tensor? Can anyone tell me? So we
Second order.
Yeah, exactly. So we're taking gradient of a vector. So the function, the property of gradient is that it increases the tensor order of any quantity. If we apply it on a scalar, it becomes a vector, first order tensor or vector, and if you apply it on a vector, it becomes a second order tensor. So it's basically, so this actually becomes dou u x by dou x, dou u y by, sorry, dou u x by dou y, dou u z by, sorry, dou u x again by dou z. Now dou u y by dou x, dou u y by dou y, dou u y by dou z. Then third component, dou u z by dou x, dou u z by dou y, dou u z by dou z. So it's basically becomes a matrix. It can be represented in a matrix. So then there's something called strain. Should write it here. Strain tensor. So strain tensor is, in terms of solid mechanics, it is defined as a symmetric component of this gradient tensor. So how do we find this symmetric? How do we break down a matrix into symmetric and asymmetric components? So I can also, in terms of initial notation, I can write this as ui comma j. So if I want to break it down, yeah, someone is answering.
It's like u I comma j plus u j comma I by 2 plus u I comma j minus u j comma I by 2.
Yes, that is correct. Yes. So this is the symmetric component, and this is the asymmetric component. So this is what we call as strain. If we if we derive its relation from the displacement. So the symmetric component of the gradient of displacement is the strain. And what about this asymmetric component? Although we don't need it here, but does anyone know what does this represent?
Rotation.
Yes, right. So this part strain is basically represents the stretch, and omega here represents the rotation. So at the end, we so our epsilon is defined as ui comma j plus uj comma I. So if we want to take its component, so this would become, so the diagonal element would be just, so suppose we want ei, any diagonal component, it would just be ui comma I. So epsilon xs becomes ux comma x, epsilon yy becomes uy comma y, and similarly epsilon zz also becomes uz comma z. But we are considering 2D for now, so we'll only care about the x and y components, and the off diagonal component would be given by this. So right now it's just epsilon xy, and this would be equal to epsilon yx because it's a symmetric principle. So this epsilon xy is basically half of the engineering strain, engineering shear strain. It is actually a shear strain, but it's similar to that, but it's not exactly equal to the uh, equal in magnitude to the engineering shear strain. So we define the engineering shear strain as gamma xy, which is twice of this value. So anyway, if we so breaking this down, if we want to represent this, so right now our shear strain tensor for 2D is basically this, right? This is all same, and so this is basically a matrix or a second order tensor. So what we do for simplicity is we represent this as a vector, this matrix as a vector. So it eases as the calculations. So we, instead of writing in terms of matrix in this and avoiding this repetition of x epsilon xy, we just represent it like this. Even if we are dealing with 3D, we could have done like this. So this kind of representation of a matrix as a vector is known as a symmetric matrix as a vector after reducing its elements is called void notation. So so if we want to represent this the strain tensor or strain vector now in terms of displacement vector, we can represent it with this formula. So this matrix here is an operator. We can treat this as an operator, which we call as symmetric gradient operator, because it doesn't give the complete gradient like del, but it gives us the so like del is also an operator which is applied on this vector u, but this gives us the complete gradient. But this operator right here, this gives us not the complete gradient, but this gives only the symmetric part of the gradient. So that's how it is different from this. It gives full grade, while this gives symmetric component only. Okay, so this is the relation between the strain and the displacement. Now, what else do we need? So for the governing equation here is this what is known as the equilibrium equation. So equilibrium equation is the sigma j comma ji comma j plus bi in terms of initial notation. If we break it down into the components, these are the two equations that we get for 2D. So as I told you earlier that since we are dealing with vector problem, so we'll have so now if for 2D if we have two variables, two primary variables, the displacement x and y, so we'll have two equations, two governing equations, coupled equations. Okay, so we again we can write this in terms of the matrix and vector system, and we'll see that we'll again see this familiar matrix, which was nothing but the symmetric gradient operator that we just saw earlier, basically a transpose of that. So using the same operator, we can define our equilibrium equation or the governing equations. Now, so we have developed an equation of the stresses, two equations for stresses, and we earlier developed the relation between the displacement and the strains. Those were three equations, I guess. Now, we now all we need to do is relate the stresses with the strain, and that is known as the constitutive relation. So, in 1D, we used to study that stress is directly proportional to strain, and where the proportional constant was this parameter called Young's modulus. But when we go to 2D and 3D, it's a so the stresses are no more scalar. Strains are not scalar. They become tensor, and since they are tensor, this material constant or this what is given as d is become this becomes a fourth order tensor. So when this fourth order tensor is operated with a second order tensor, it gives another second order tensor, that is stress. So in initial notation, we can write this as d I j k l. So there are four free indices here: I, j, k, and l. So this represents a fourth order tensor, and of course, for if this be a this fourth order tensor for in 3D is supposed to give 81 components. So there are a lot of material constants here involved here, but luckily we it due to the symmetries involved in the tensors sigma and epsilon, these reduce by a large number, and for if mostly we consider isotropic case for with the linear elasticity, so then we are these components are reduced to just two components. So in general, it can be the Young's modulus and Poisson's ratio, but there are other constants also, and we just need to know that two constants, and rest of those can be derived. Now, to get this D matrix in terms of these two components, we need to know the condition for this. So first we consider a plane stress condition. So it's an assumption. So in plane stress assumption, we assume that the stresses in z directions are zero. So this essentially means that the thickness of domain is negligible. It's kind of a lamina. So there D is defined by this formula. And there's another assumption called plane strain, where the strains in the z direction are assumed to be zero, and that is possible for an infinitely long for a domain which has infinitely long thickness. So, and mind it that for plane stress, the strain in z direction would not be necessarily be zero, and for plane strain, the stress in z direction would not necessarily be zero. And so D here is defined by this formula. Okay, so okay, now if we sum up all this, we can define this the elasticity problem by this statement. So we write the equilibrium equation, and we define the boundary condition. So we the as usual with, a part of boundary where we specify the Dirichlet boundary condition, and there's another part of boundary where we specify the Neumann boundary condition. So Neumann boundary condition here is known as traction, which will again have two components, Tx and Ty. So now taking weak form of this vector equation. So this equation here, this is the vector equation. That means it will have components. There will be, so for 2D there will be two equations. So when we are taking weak form, earlier we used to multiply a single scalar weight function to take the weak form. Now we'll have a vector weight function. So we take dot product of this the vector equation. So we represent the vector equation by a vector r, that is nothing but the residual. So there will be two components for residual, one for each equation, and we take the dot product with the weight function vector. So we have wx rx plus wy ry, and that similarly we'll have a gradient a divergence component, and so we need to reduce the differentiability requirement. So we do form integration by parts, and we get a boundary term, and it's all the same as we did before. There's nothing new. Okay, so now left hand side we're left with this term, the gradient of this weight function dotted with the stress. Okay, so okay, so if we take the gradient of the x component of the weight function, we will have these component wx comma x, wy comma y, w and wxy. So if we when we rewrote this term combined here, we'll have if we can reduce it in this form, and finally we can represent the vector of the weight function, uh, the gradient on the vector weight function using the symmetric operator that we saw earlier. So like uh, when this symmetric gradient operator was applied on the displacement vector, what we got was strain, right? Uh, Now if we apply this on the weight function vector, we'll give we name it as the virtual displacement operator. So this is the virtual displacement, and again that we know that sigma is equals to d times epsilon. So and epsilon can be written as, right? I'll just leave this bar here, remove there for consistency. So finally, we're left with this term here. So this is our final weak form. I hope this is clear here. If there's any doubt, you can ask me. And so now, next thing is to discretize this. So we have our weight function vector WE and the displacement vector UE. So we like usually we want to define it as a as the uh, linear interpolation of the shape functions or the approximation functions. So we assume a quadrilateral element, and so we'll have four approximation function for corresponding to each node of the quadrilateral element. So we can define this vector of a vector u as this the following. So each of these column vector represents the displacement in x and y direction for each node. So these are for so these two are for node 1, node 2, node 3, node 4. So we can represent this displacement vector as the nodal displacement in each direction for the quadrilateral element like this. So this can be simplified as the multiplication of this the n matrix with this vector alpha u. So now next thing is to calculate so this give us the representation of UE in terms of the shape function. Now what we need is gamma this del is operated on UE. So del is we know. So if we solve this, we multiplied these two matrices. We'll have this 3 by 2 and 2 by 8 matrix. So ultimately we'll get a 3 cross 8 matrix, which we can represent right as BE. So ultimately, this gradient operator, symmetric gradient operator applied on UE can be written as represented as the product of BE with these nodal values alpha E. And similarly, the same thing we can do for WE. So if we want to represent WE, we'll do the same as we did for UE. And if we want to represent del SWE, we'll do the same. So here we have B matrix and here we have N matrix. So finally our equation becomes like this. So our stiffness matrix for an element would be the product of the transpose of B into D into B. And force vector is pretty straightforward. The product of any with the vector B and product of any with the vector T for the bound term, boundary term. Okay, so here till here we represented the our weak form into discretized form by representing the solution in terms of the approximation functions using these operations. Then next thing is to map these standard element map the given random element to the standard element. So for example, if we have any random quadrilateral, we can map this to the master element or the standard element minus 1 minus 1 1 minus 1 1 1 minus 1 1. So for that we have to calculate the mapping, then the Jacobian, and we had done this for scalar problems, that this mapping is represented by this formula. So if you multiply uh, if we calculate this n matrix as we like this for the standard shape functions in terms of eta and xi, and if we multiply it by this inverse of the transpose of the Jacobian or the transpose of the inverse of the Jacobian, we can get our this n matrix for the given coordinate system. This the formula for this J inverse transpose is this. and this will give us the n matrix, right? This over here, this matrix. But how do we get the B? So once we get this, we just need to reshape the n matrix that we got into this B matrix using the. So if you see this n matrix here and this B matrix here, is so n is just reshaped to right B, right? Okay, so this concludes whatever we had done this week, and after that we try to solve some problem that we'll see in the discussion later. So if there's any doubt regarding this, we can discuss it now. So if there's no doubt, then shall we move forward? Okay, then we'll move on to the problems. So problem number one: which of these elements are valid FEM elements? So would anyone like to answer? Which are valid and which are not? Anyone any guesses? What about first element?
Think except D all are valid. I think.
Okay, so you say D is not valid.
I think yeah.
Why is it?
If I remember correctly, the angle should like angle between the lines should not be greater than
Yes, right.
some the angle that is there. Not
Theta
good.
is actually greater than 180 degree. So that is why. So what will happen if we use this element is that the Jacobian would give the Jacobian, the determinant of the Jacobian would be negative. So uh, this would cause numerical issues. Okay, so what about first element? First option,
It is okay. We can use that.
right? What about second?
Second also.
Second, there is kind of issue. So this the aspect ratio should not be too large.
Okay.
So if we use this kind of element, the determinant of Jacobian would be uh, almost tending to zero. So this would also cause numerical issues. So it's better to not use this element. What about C?
Fine.
Yeah, C is fine. It's just a quantitative element. Okay. So consider the Poisson's equation given here. Calculate the stiffness matrix and force vector for a triangular element with nodes 0, 0, 1, 0, 0. Okay, so so first of all, what do we have for domain here? This is our domain 1, 0, it's node 1, node 2, then node 3 is 0, 1. So if we remember that this is the master element for triangular elements. So can anyone tell me the approximation function for this kind of element? Any idea for the approximation functions? Or do you want me to derive them? I hope we don't need to derive them now. We have done it a couple of times.
So we are seeking for shape function in parametric space, right? Like 1 minus
Yes,
theta plus neta.
yes, yes, yes. So this is for node 1, right?
Yeah. No, node 1. Ah, yeah.
What about 2 and 3?
I think zeta neta.
Yes, correct.
Side.
Okay. Now to solve our problem, what should we do first? Anyone?
Write the weak form.
Yes, exactly. So then we perform integration by parts, or we apply that in the 1D we used to do that. Now in 2D we call it as cost divergence. So what do we get here? So let us skip the boundary term for a while. We don't need for this problem. So this would give us our stiffness matrix. Okay, so we need to approximate 2, right? So what do we usually get? The end we'll get gradient ni dot gradient nj, sorry u. So gradient ni means a vector ni comma xi ni comma ta. So this is being dotted with gradient of nj. What do we get here? So anyways, this here is our stiffness matrix Kij, and this here is our force vector Fi. So let us first find Kij. This is, so if we open the dot product, we'll get, right. Okay, so what is our K11? So we have N1 xi, N1 xi, and 2, sorry. So I made a mistake here, right? It should be eta. Yeah. And then again N1 xi. So it would be N1 xi, N1 xi, N1 eta, N1 eta, comma eta. I mean. So we have, we have, yeah, N1 comma xi squared plus N1 comma eta squared. So what is N1 comma xi? Oh, I have written N here, right? And here I have written psi. I should maintain the consistency. So derivative of N1 respect to xi is -1, right? So we have minus 1 square, so it becomes 1, and derivative of n1 with respect to eta is also minus 1, right? This is also now minus 1 square is plus 1. So we are left with the 2. So this is basically integral over a triangle dx dy. So it's a painful job if we have to calculate the integral for a triangle. For I think square domain it's quite easy, but for triangular you have to uh, assume a strip and write the limits in terms of x, y. It's painful job. Luckily, I think we have some direct integral formula for over triangular domains. That is in terms of the area of the triangle. I don't remember that, so we can leave it to this. Should be 10 times of the area of this triangle dx dy. So I don't remember that formula is something in terms of the area of the triangle. So leave it to this. We'll just find k12. So that would be uh, n1 comma xi n2 comma xi plus n1 comma eta n2 comma eta. So this is equal to, so n1 comma xi is minus 1 and n2 comma xi is plus 1. So we have minus 1, and then we have n1 comma eta is minus 1 and n2 comma eta is 0. So we don't have, so this whole term becomes, second term becomes 0. So we are, all we are left is minus 1. We have minus 5, then again the integral. So there's a 2 right here, just right here. We are left with minus 5 integral of the triangle dx dy. I think this should give the area of the triangle only, I hope. If anyone knows this answer, you can speak up. I don't want to solve integrals here. So then we also do one more component k13, that is 5 times integral over the triangle n1 comma xi n3 comma xi plus n1 comma eta n3 comma eta. So n1 comma xi is minus 1, n3 comma xi is 0. So this term is 0. And n1 comma eta is minus 1, n3 comma eta is plus 1. So again we'll have same term. We'll have minus 5. Yeah, I think this should be area of the triangle. So if area of the triangle is, I think minus, it's half. So all we have minus 5 by 2, 5, minus 5 by 2 and 5 by 2 here. No, it's 5. Okay, anyways, so we can get the all the components for the acceptance matrix like this. Now next thing is to get the force factor. So force factor is integral ni. So this is pretty straightforward. So this is equal to n1, which is 1 minus eta minus I. I'm sorry, this I have written dx dy, it should be eta zeta. Before also. Anyway, either we can just write 1 minus theta minus zeta is 1 minus x minus y. It's the one and the same thing. So we'll not evaluate this, but we can find this, right? Or we can just use Gauss quadrature rule also. So if we use 0, yeah, we can use Gauss quadrature. This can be equal to 4 times the value of this function at 0, 0 comma 0. This will be equal to 4. I hope that is all. Then F2 is and F3 would be okay. So this would be the 3 components for the force vector. We can calculate them like this. All right. So I hope this is clear. Shall we move on to the next problem? Okay. So next problem is solve the previous problem for the quadrilateral element with nodes -1, -1. So this again is the standard master element for the quadrilateral elements. So we know the approximation functions here. Okay, so these are the approximation function. So we had derived the weak form the uh, equation for the difference matrix and force vector before, so we can use them directly. By the way, this this formula here is not valid. I made a mistake here because we need to change the limits of the integral uh, to -1 to +1. So we need to transform the domain from triangular domain to this rectangular domain here. So ignore that. we have ni comma xi nj comma xi plus ni comma eta nj comma eta. So what should be a k11 n1 comma psi n1 comma psi, right, that or square, right, plus n1 comma eta square. So n1, the derivative of n1 respect to psi is minus of 1 minus eta by 4, right? Okay, start. And this thing is squared. Then we have derivative of n1 with respect to eta is this minus 1 by 4 1 minus psi thing squared. So this thing I think we can do for, using Gauss quadrature, because now our domain is the master domain for where we can apply the Gauss quadrature rule for 2D. So we can just use the formula 5 into 4 into the value of the function at 0 comma 0. So this first term becomes minus 1 by 4 squared, that is 1 by 16, and this is 1 minus eta square, that is becomes 1 square. And then again this term also becomes 1 by 16 times 1 minus zeta square, that zeta is 0, so it becomes 1 square. So 5 into 4 into 2 by 16. So we have here 5 by 2. Then what's k12? So can anyone help me here? Would anyone like to try? Okay, let's do different terms this time. Sorry. I hope my audio is clear, right? So let's do k23 this time. So n2 comma xi plus n3 comma xi plus, sorry, not plus, multiplied, plus n2 comma eta into n3 comma eta. So what do we have here? So derivative of n2 with respect to xi is anyone. So this is 1 by 4 times 1 minus eta, right? Or 1 minus eta by 4. And n3 with respect to xi is 1 plus eta by 4. This sum with n2 comma eta. So this is minus of 1 plus xi by 4, and n3 comma eta is 1 plus xi by 4, right? So what do we have here? So if we apply cost quadrature, if I into 4 times the value of the function at 0 comma 0, we're just using one point Gauss quadrature rule. So first term becomes 1 minus 0 by 4, 1 plus 0 by 4, it becomes 1 by 16. And second term is minus 1 minus 0, that is minus 1 into uh, 1, 1 plus 0 is 1 by 4, it becomes minus 1 by 16. Good. So this term becomes 0 essentially. That's interesting. Don't know how accurate this is. Okay, so can we try for k 1 4? So we have n1 comma xi n4 comma xi plus n1 comma eta n4 comma eta. Okay, so n1 comma xi we've already calculated before, minus 1 by 4 to 1 minus eta, and n4 comma xi is also minus 1 minus 1 minus 1 plus eta by 4. These minus minus will get cancelled. And we have n1 comma eta is minus 1 minus eta by 4, and n4 comma eta is 1 plus eta by 4. Okay, so again we apply the Gauss quadrature, 5 into 4. So 1 minus eta into 1 plus eta by 4. So eta equals 0 will be 1 by 16. And then we have minus 1 into 1 minus eta, that is becomes minus 1 by 4. And we have 1 plus eta by 4, 1 eta is 0, 1 plus 0 by 4, 1 by 4. Again we have minus 1 by 16. This term also becomes 0. This is okay, so we're getting 0, quite 0 values. I don't know how accurate this is, but anyway we are just trying. The important thing is we should know the procedure. Okay, we can try for some force matrix values. Oh, this was straightforward. So F1 would be 1 by 4, 1 minus theta, 1 minus psi, 1 minus theta, and we apply the cos quadrature. So eta equals 0, psi equals 0, eta equals 0 would give us 1 into 1. So we have just have 1 here. F2 would be again 1 by 4. So 1 plus the right. Again we apply cos quadrature. We have 1 and 2 1. So we'll again get 1. F3, you see whatever the sign between these function 1 plus minus theta, 1 plus minus theta, we'll always get 1 here. And similarly F4 would also be. So all the terms in the force vector are 1. So I hope this was clear. If there's any doubt, we can discuss. All right, then shall we move on to the next problem? So if the displacement field is given by this vector, find the deformation gradient, also find the strain tensor. So we have given the displacement vector as this. So this is ux, uy, uz. So can anyone tell me what would be the deformation gradient? Can anyone try and evaluate the values? So what are these values? Dou ux with respect to dou x is 2xy, right? And dou ux with respect to dou y will give x square. Then dou ux with respect to dou z is 0. There's no z term. Then dou uy with respect to x is 0. Dou uy with respect to y is 1. And dou uy with respect to z is 0. Then dou uz with respect to x is y. Dou uz with respect to dou y is x. And dou uz with respect to dou z is 0. So this will be our deformation gradient tensor. Now we need to find the strain tensor. So strain tensor is the symmetric component of this tensor, right? So how do we calculate that? Any idea? How do we calculate that? Anyone, any guesses? Anyone, any guesses? So to get the symmetric component of any matrix, what we do is just the transpose of this divided by 2. So we take this matrix 2xy, x square 0, 0, 1, 0, yx 0, and we add its transpose. That would be 2xy 0 y x square 1 0 0, 0, 0. So if we add these matrices, we have 2xy plus 2xy becomes 4xy, this becomes x square, this becomes y, then this becomes x square, becomes 2, becomes 0, and we have y, x, and again 0. So ultimately our straight tensor is 2xy, x square by 2, y by 2, x square by 2, 1, 0, y by 2, x by 2, and 0. So this will be a uh, strain tensor. Okay, I hope this is clear. Okay, then let's move on to the next problem. If there are no doubts. So for the previous problem, find the stress tensor for both plane stress and plane strain assumptions. Consider E equals to 200 and nu equals to zero point 0.3. So first we in order to find stress, stress is given by this. So we know this, and uh, we need to find D and then epsilon. Sorry, sigma bar. So first we consider plane stress. So for plane stress, what is the formula for D? Anyone? Anyone can help me? The 1, nu, 0, nu, 1, 0, have 0, 0, and this is I think 1 minus nu by 2. Can someone correct me if this is wrong? Yes, match it. Yeah, I think this is correct. So this is our D matrix for plane stress. We'll evaluate it. 200 upon 1 minus 0.3 square. 0.3 square is 0.09. So 1 minus 0.09 is 0.91. Then we have 1, 0.30, 0.310, 0, 0, and 1 minus 0.3 is 0.7 divided by 2 is 0.35. So if we simplify this matrix, we have 200 divided by 0.91 first. That's 219.78. So we have B equals 219.78, and this is multiplied by into 0.3, we have 65.93, and we have 0. Then again we have 65.93, then we have 219.78, we have 0, then we have 0, 0, and 219.78 into 0.35, we have 76.92. Okay, so for plane stress we have this D, and okay, so we have xy in terms of xy. So we need to know the coordinates for xy, right? Otherwise we can't get a numerical value. So we can just take x equals to 1, y equals to 1. So our stress is this matrix multiplied by, so 2x would be 2, x square by 2 would be half, 2, 0.5, y by 2 is half, and we have x square by 2 is half, 1, 0. Oh, okay, okay, okay. So since we can reduce this matrix, right? So we'll just uh, reduce our epsilon into void notation. So in void notation, what we write, epsilon xx, epsilon yy, epsilon xy. So anyways, we don't need the z components. So we have 2, yy is 1, and xy is half. So we'll just ignore the z components for now. So we have this vector here, 2, 1, half. So the first term would be, you're welcome to help me here, 219.78 into 2 plus 65.93 into 1, and the next is 0. So we have 505.49, and we have 65.93 into 2, and 219.78 into 1, and third term is again 0, get 351.64, and then last term is just 76.92 into 0.5 is 38.46. So this is our stress in x direction, this is our stress in y direction, and this is our shear stress xy direction. So this is the stress value for plane stress condition. Now what about plane strain? What is the formula for D now? I hope this is correct. Please check. 1 plus nu minus 2 nu. Well, okay, this is wrong. This change here is only on the diagonal elements. So minus nu is added to each of the diagonal element here. Sorry. Okay, so we have 200 upon 1 plus nu is 1.3 and 1 minus 2 nu is 1 minus 2 to 0.3 is 0.6 into 0.4. Here we have 1 minus 0.3 is 0.7, 0.3, 0, 0.3, 0.7, 0, 0, 0, and 1 minus 2 nu is 0.4 divided by 2 is 0.2. So we simplify it. We have 2, sorry, 200 divided by 1.3 into 0.4. We get D equals to 384.61 into 7.30 0.3.700.2, which simplify becomes 384.61 to 0.7 269.23 to 0.3 becomes 115.380. This is 115.38, 269.230, 0, 0, and multiply by 2.2. This is 76.22. So now what is the stress here? This multiplied by a strain vector 210.5. So we have 269.23 into 2 plus 115.38 into 1 and then 0. We get 653.84. Then we have 115.38 into 2, and we have 269.23 into 1, and then 0. We get 499.99. Then we have just 76.92 into zero point 0.5, 38.46. Okay, so this is our stress in the x direction, stress in y direction, and this is our shear stress in xy direction. So this is our stress vector for plane strain condition. So note the difference we have. It's quite significant, except for the shear stress that is same for both the cases. Because for this condition, I think we'll also have the ZZ stress component, stress in ZZ direction. That I think would be equal to, I think, minus nu times stress in x plus stress in y. Not sure, something like this. Okay, I hope this is clear. If there's any doubt, you can ask. Okay, so is there any doubt here? So can you move forward? So the next problem is for the standard quadrilateral element or the master element, find the force vector if the flux of magnitude 10 is specified at the right and top face. So this is our master element. So we need to evaluate the the Neumann boundary term. So we are given Qn. So we break it down into, okay, so yeah, so we break it down into uh, four integral for each edge, and since there's no flux on the bottom and left face, so we'll only have 2 3 and 3 4. Okay, so we first evaluate on the face, right face. So for that we have this element 2 3 with node 1 minus 1 and 1 1. So we map it to 1D element from minus 1 to 1. So after this mapping, we evaluate this f cap for this element. So our Qn is 10 Ni. Okay, so for a 1D element, N1 would be 1 minus xi by 2, N2 would be 1 plus xi by 2. So this would be, it's better to write like this. So applying Gauss quadrature, we have 5 into 2 into 1 minus 0. This gives us 10. And F2 would be, so this again would be 5 into 2 into 1 plus 0. This is also 10. So our force vector, main force vector would have four components here, right? For a quadrilateral element. So the contribution of F1, which is F1, this is node 1. So node 1 here is, we'll go in order. Node 1 here is edit for 2 and node 2 here is edit for 3. So we'll have F1 cap added here and we have F2 cap added here. So our F becomes After this operation, f would become 0, 10, 10, 0. Okay, fine. So next is we take the top face 3, which is 1 comma 1, and 4, which is minus 1 comma 1. So we map it to our 1D domain to z equals to minus 1, z equals to plus 1. So now our phi again is to 1, 10 ni t z. So f1 is, so it's the same, f1 again here would be 10. Sorry, I did a mistake here. Okay, no, that's fine. It's right. 5, this is 5. And this next 2 is the weight function. So we'll get 10 again here. And f2 cap would also be 10. So now this local node for this element here, 1 is for 3 and 2 here is for 4. So in our f vector that we had before, 0, 10, 10, 0. So now f1 would be added at 3 and f2 would be added at f cap 2 is added at 4. So finally our force vector would be 0, 10, 20, 10. Okay, so this would be our final force vector due to these two Neumann boundary condition on this element. So I hope this was an understandable demonstration on how to apply the Neumann boundary condition in 2D elements. Okay. Okay, so we can move on to the next problem now. Consider a bar with uniformly distributed heat source Q is 5 watt per meter. The cross section area of the bar is zero point 0.1 meter square. Ignore this. The thermal conductivity K is 2 watt per degree per meter. The length of bar is 4 meter and boundary conditions are at x equals 0, t is 0 and x equals to 4. The flux is 5 watt per meter square. So this was originally a 1D FEM problem that we solved earlier. So now let us try solving this problem using a 2D FEM code. So solve this problem using 2D FEM solver considering domain of size 4 meter by 1 meter. So we can take, instead of a 1D rod, what we can do is we can consider this bar of 1 meter, 4 meter as 4 by 1 meter. You can assume its thickness is 0.1 meter, so that its area of cross section would be 0.1 meter square. So we can break it down into 4 elements. So we have node 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is our element 1, element 2, 3, element 4. So we have restricted boundary condition at this phase, and we have a Neumann boundary condition at this phase. It's not Q actually, it's flux. Okay, so we'll try to use the MATLAB code for this. So let me share my MATLAB screen. I hope the MATLAB screen is visible. So firstly, we need to define the mesh. Okay. So we had four elements. So first of all, we have 10 coordinates. So first is 0, 0. Then we have 1, comma 0, 2, comma 0. Sorry, it's better if I just add 1, comma 0. Then we have 3, comma 0. And then we have 4, comma 0. 1, 2, 3, 4, 5. Okay, then we have 4, comma 1, comma 1. We have 3, comma 1, 2, comma 1, and we have 1, comma 1. So we have total 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes. And for connectivity matrix, we have we have four elements. So first is 1, 2, 9, 10. 9, 10, 1. Then second is 2, 3, 8, 9. 8, 9. Then we have 3, 4, 7, 8. 3, 4, 7, 8. Again 3. Then we have 4, 5, 6, 7. 4, 5, 6, 7. Back to 4. So these are our four elements. And what are the boundary conditions? So for we have to define for each element. So for as we had seen before, for boundary condition we define we write uh, the boundary condition for each element. So for first element we have no boundary condition at the first phase, then no at second, and at third, but we have a decision boundary condition at the fourth phase. Fine. Then we have for second phase we don't have any. 0, 0, 0, 0, 0, 0. Okay, so for third phase again we don't have any boundary condition on any phase. Then fourth element we have 0 at first, and we have a Neumann boundary condition at first phase, sorry, second phase, and then no boundary condition in third and no boundary condition in the fourth phase. So now we define the conductivity for us is 5. So we consider a constant conductivity of 5.0. And sorry, conductivity here is 2. Then our heat source term is 5. So we define the values of Neumann boundary condition. So I think we just have one Neumann boundary condition, that is 5. we can comment the rest. Then the decision boundary condition is 0. At t equals x equals 0, we have t equals 0. So we have number of degree of freedom per node is 1. Number of nodes per element is 4. Degree of freedom per node is 1. So sorry, this is degree of polynomial. This is 1. Then we have Gauss point, same. You can use the same thing. And I think the rest of the code should work fine. Hopefully, let's see. Okay, so we got some result. It seems to be okay. Yeah. So we have 0 at 0. That's right, and we have a increasing value. So let's see what's the order. Let's see the result. 3D. Yeah. So this is kind of a parabolic function as we expected. The maximum value is coming around here. Okay, so I think this is actually similar to what we solved it you in the 1D problem. Let me just check. And we did that 1D. Okay, so I don't have solution right now, but yeah, the solution looks convincing now. So I'll stop sharing the screen here. Let me get back to. Yeah, let's get back to the problems here. Yeah, so yeah, we transformed this 1D problem into a 2D problem simply and got the solution using our 2D FEM code. So that was pretty nice. So can we go for one more question? Yeah, we have time. Okay, so this question. Consider a problem shown in the figure. Which of the following options is true? So we have been given this domain which is meshed it using triangular elements, and the node and the element numbers are marked. So the numbers in circle are the element numbers, and the other numbers are the node numbers. So in the options, so we have these options here. So in these options, Qn represent the distributed load along the boundary of the element E. Gamma is the boundary of the element E. S is the distance along the boundary, and phi Es is the interpolation function for the primary variable. So which of these is true? First of all, it's the option A is integral over gamma 5, that is this element 5 over here. Qn into phi I5 S ds. So so this integral equals 0. Is it true or not? Anyone would like to answer? So so if we take this integral over gamma 5, this can be broken down into the integral over the edge 3, 4, 4, 5, and 5. So so we 3, 4 is an internal edge, it's 0, but 4, 5, and 5, 3 are outside edge. So there would be, there is Qn prescribed here, so these won't be 0. So this will not be equal to 0. So this is wrong. And then integral over 4 5 q and 5, this is also not equal to 0. So this is also wrong. Then integral over 6 7, 6 7 is this phase here. This is also not, this is also on the internal phase. So this is also not true. Then we have integral over the element gamma 2. So if you see the each of these edge of the gamma 2 are the internal edge. So there is no Norman boundary term here. So this is definitely going to be 0. So this is the correct option here. So I hope this was clear. So I think we are out of time now. So we can conclude the session here. And if there are any more doubts, we can quickly discuss them before finishing the meeting. And if there are no doubts, then you are welcome to leave the meeting. Okay, so if there are no doubts, then thank you so much for joining the session. We'll meet again next Tuesday. Bye.